One of the things that I talked about in one of the previous videos is the pitfall of what I like to call standard recursion. So remember with the add example, we said we would have something like 3 and then some really big number like this, and then we'd have another so this would be the first thing on the procedure call stack, and then we'd have another where the number is one less because of how we do the addition. Well, with the way that we wrote it, the in parameter, this one, is the one that's decreasing towards 0, but for the purposes of the example, we'll just say that it's this one that decreases to 0. So remember, the issue was that the stack frame has very little memory, and if we overflow the stack, then the program will crash, which is not good, and we'll get something called stack overflow error. So last time I told you to think about possible solutions to this particular problem. Now, why exactly do we need a procedure call stack? Well, if you remember, when we're doing those addition operations, so we have something like, 3, 4, then 3, 4, or sorry, 2, 4, 1, 4, 0, 4, then we get 4. But remember, outside of all of these, we have that plus 1, that add 1 operation, which then becomes something like this. And here we have all those plus 1s that then cascade back into, we have 5, and then we have 6, and we have 7, of course. Okay? So we did this kind of in reverse of the call stack, but you can kind of imagine what's going on here. When we have this stuff that's left to do, remember, we said that was called unwinding the stack. Unwind the stack. Remember, we said this was the recursive decomposition, and this is the base case. Okay? So the problem or the issue here is that with the good thing about the call stack is that we know, or Java knows, where to return to or what is left to do after we hit the base case. So the underlying issue here is that because there's that plus 1 outside of the recursive call, or rather it's that series of add 1s, there's stuff that's left to do after the recursive call. And that's the problem here. At least that's seemingly the problem. So the solution that might be intuitive is, why not just not have anything left to do? Right? If there's no plus 1s outside of the recursive call, then there's no need for there to be a stack frame, or for there to anything. If there's nothing left to do, then there's no need to remember the context of the previous stack frame on the call stack. Okay? So what I've just described is something called tail recursion. And essentially what that is it means that there is nothing left to do after a recursive call is made. So for example, if we have a method called static int foo, then inside of this method we might have some things, but if we have a, let's say, a return, and then we have a recursive call, or we have anything, wherever there's a recursive call, there's nothing that is around that recursive call. There's no operations, there's no plus 1s, there's nothing. Okay? So when we're writing tail recursive methods, usually this is going to look something like this, where we have the recursive invocation followed by absolutely nothing on either side, except for, of course, the return. But there's no, again, there's no plus 1, there's no 1 plus, there's no method calls around it, there's nothing. Okay? So in theory, this could prevent us from needing the call stack in general, because if you think about it, like, let's say that we make a function or a recursive call to foo, and then if there's nothing left to do, we could just replace this stack frame with a new one with the updated parameters. Right? And then when we're done with that one, just remove it and then and then push the next one. Okay? So let's see what that looks like with factorial. Okay? So when we're writing a tail recursive factorial method, the idea is that we want this n times to go away. We want that to disappear because that's the thing that we have to do when the stack is unwinding. Okay, so how do we get rid of that? Well, we first should write a method called static int factr. Okay, now interestingly, our case analysis is going to stay the same. So if 0, do something, otherwise do something else. Now, we know that because this method is tail recursive, we're going to have something like this. So we can immediately type return factr and then something here. This is exactly what it has to look like for it to be tail recursive. Okay, there can't be anything outside of the recursive call. Okay, so the issue now is how do we emulate the behavior of doing factorial in a tail recursive sense? Well, why not use a second parameter and accumulate the result as a parameter? Okay, what do I mean by that? Let's take factr, and let's suppose that it has a second argument that starts at 1, and we pass it 5. So we want to compute fact of 5, which we know is going to be 120, but how might we do that? Well, let's say that in between each recursive call, we're going to decrement the value of n, because we want this to head towards the base case, of course, but we're going to multiply the value of n by the accumulator. Okay? So on the first recursive call, we see 5 and 1. On the next recursive call, we're going to multiply these two values together. So we're going to get 5 times 1, which is 5. Okay? On the next recursive call, because we're still not at the base case, we're going to get 3, and then we're going to multiply, again, these two things. So we're going to multiply 4, and we're going to multiply 5, which, of course, is 20. Then we're going to multiply what? We're going to multiply 3 by 20. You see where we're going with this? Now, hopefully you've already you've seen this coming, but we get down to here, we're going to do 2 times 60, which, of course, is our amazing 120. And then we're going to do one more to hit the base case, so then we're going to do multiply 1 by 120, which gives us 120. Now, what happens when we hit the base case? Remember, there's no unwinding to do, so there's no action left to build the result as a series of recursive calls. Therefore, we should just return the thing we've accumulated. So, when we hit the base case, just return the accumulator. Okay? Just return the accumulator. Alright? So now that we've seen how we can do this, let's turn this into a programming, let's convert this into code.